All right, so in this video, we're going to continue discussing line integrals. And to start, it's going to be line integrals now with respect to x, y, and z. In all of the previous examples, we've started ds, s for arc length, and then we've transitioned into t's. Here we're going to be starting with respect to z, and the dx and the dy cases are identical. So I'm just going to show you this one, and then we'll take a look at an example. So we're going to consider the line integral here with respect to z. And if you'll remember, dz dt equals z prime t, which means that dz would be z prime t dt. And so what I've done is I've allowed now to create a line integral with respect to t. So we'll still be on a to b. Our function f will be now with respect to t, so that'll be x of t, y of t, z of t needing to be plugged in there. And then the dz would be the z prime t dt. So z prime t dt. And so again, this was the example for dz. If we were doing x and y, it would be the same, and that would be an x prime dt. If we did a y, we'd have a y prime dt there, all worked out in a similar way. All right, so we're going to take a look at this line integral here and how it's presented. You can see also that it's going to have our dx in here and our dy in here. The curve C that we're going to look at is I'm actually going to present it in a different way. We're going to knock out two things here in this example. We're not only going to talk about line integrals with respect to x and y, but we're also going to talk about having this closed curve that I'm going to draw. So our curve C, I'm going to have as this line right here and this semicircle right here, where we'll call that -5, we'll call that 5, and then we're also going to put in some orientation. We're going to put in some orientation so that our particle is traveling around this closed region in this way. And so what's happening is we essentially have two curves. We have this bottom one, maybe I'll call that C1, and this top one here, I'm going to call C2. And bottom line is, if you have, or if you want the line integral over curve C, we can simply do one of them and add it to the other and still get the overall total result. So essentially, this is two problems in one. I'm going to go along this curve first, and then I'll go along this curve second. So what I guess I'll start with here would be C1. Now I'll need, and C1, by the way, is just going to be y equals 0. So I'm going to need a parameterization for that. So my smooth parameterization of the curve would be x equals t and y equals 0. Of course, though, we're bounded between 5 and -5. For curve 2, for C2, and I didn't mark this up here, but I meant to, that's a 5, which means that our y equals square root of 25 minus x squared would be our curve, which means that x squared plus y squared equals 25. And if you guys remember from Calc 2, the parameterization for this would be x equals 5 cosine t and y equals 5 sine t. And this is where t is going to be bounded between 0 and pi in this case. Not 2 pi, pi, there we go. So let's go ahead and get this first part set up. So the first integral, I'm going to go from -5 to 5. Now, as you can see, we've got our y dx, and I'm going to need to write that in terms of t's. So for y, that's going to be this guy. So I've got a 0. And then for the dx, that's going to be the x prime t dt. So the derivative of x with respect to t is going to be 1. So I'll put a 1 there. And then followed by the dt. Then I'll have a minus, and I'm going to drop another integral symbol in here just so that it's a little more, I guess, consistent with what you might expect. So -5 to 5 there. And again, that minus is this minus. Now I'm going to drop my x in there. My x is a t. So that's going to be a t. And then times the dy. Well, the dy is going to be the y prime t dt. And the derivative of y is going to be 0. So that's going to be a 0 dt. So again, the reason I dropped that second integral symbol in there is because it was a little more apparent now with our dt actually being the differential dt. So what I'll do is just go ahead and maybe simplify that a bit for you. Well, honestly, it's just going to boil down to a 0 dt, so that thing goes off to 0 to end with. All right, so that was C1. For our second curve here, this is going to be 0 to pi, and we're focusing on these things right here now. We've got our y, which is going to be 5 sine t, so 5 sine t, followed by x prime t dt. So x prime here would be a negative 5 sine, so a negative 5 sine, and then our dt, minus from 0 to pi. So that minus, again, is the same minus as that. Now we have our x, y prime dt. So the x would have been 5 cosine t. The y prime would have been 5 cosine t. And then we have our dt. And if you're actually going to go ahead and integrate this out, you could simplify it down to one simple integral, where you'd have this inside right here minus this inside right here, and then one single dt. So I'm going to shrink this down so I can fit that in there. So that's going to be a negative 25 sine squared, negative 25, there we go, sine squared t, and then minus a 25 cosine squared t dt. So again, a couple big takeaways from this problem. The first one being that if we have this closed curve or closed region like this, that we can simply treat them separately, add them together, and you'll get the desired result. And so the second part, though, is the fact that now we're with respect to x's and y's, and so the x prime dt would be your dx, the y prime would be dt would be the dy. And then once you get to your parameterization, it really is just a matter of substituting stuff in. So not too difficult to follow, assuming you stay organized in your parameterizations. All right, so now we're ready to talk about the flux of vector field F across C. And so before I get into that, though, I want to point out the blue stuff here in the middle of the screen. Flux in general is probably a new idea for most people, and just really think about it as net inflow minus net outflow, in that what it gives us is the quantity which passes through the surface or substance. So anytime we think about flux, we're talking about the magnitude, the direction of a flow through a substance or a property. And so that's usually first seen when you get to physics and you talk about electricity and magnetism. You'll talk about flux. But just to give you a basic idea of what it is, that's where we stand. Now, in terms of the math behind it, you'll see this from time to time quite a bit in your book, even though it's going to simplify down to this. But it's your typical single integral over curve C, f dot n ds. The way that this breaks down then is going to be your flux integral that you see here. And that little circle on there usually denotes orientation. Depending on the textbook, sometimes you see it, sometimes you don't. Sometimes you'll see a little arrow there, a little hook there, noting the direction of the orientation, many times implied counterclockwise. But just don't be surprised when you see that. That's generally used for a line integral and will help with orientation, as we saw in the last example, in fact. And then otherwise, it's pretty straightforward. PDY minus QDX. The vector field F is PQ, and then this N that we talk about up here that I've already simplified down is just going to be an outward pointing unit normal vector on C. The outward pointing is going to be helpful with orientation as well. So I'm going to go ahead and erase this or clear the screen, and then we'll take a look at an example, and you'll see, once again, if you're comfortable with the notation, it's just a matter of plugging stuff in. All right, so the example we'll look at here is we're looking for the flux across, or of F across the curve here, C. in the XY plane. And so this was the equation that we set up in the last screen. First thing that I would probably want to go ahead and do is parameterize the curve. And so that curve is a circle, just like in the last example. Pretty easy to parameterize this one, centered at 0, 0 with a radius 1. We'll call that cosine t. We'll call that sine t. And we've got our parameterization then. And this would, of course, be between 0 and 2 pi, since it's the full circle. So from there, if I take my r prime, that's going to give us a negative sine t and then a positive cosine t. So the best thing to do, again, is when you're asked to do something, put down the equation for what you're wanting to compute. That way you can better identify it. We were given our p and our q. This was our p right here. This was our q. And then what we found was the dx and then the dy. So when we put this all together now, using our 0 to 2 pi single integral, I'm going to start with my x minus y. So that'll be a cosine minus a sine. So cosine t minus sine of t, followed by the dy, which was cosine of t, minus q, which was x from up here, but we can't write an x, we have to write a cosine. So let me write that to be cosine of t, followed by then our dx, which would have been negative sine of t. And so all of that combined with a dt on the back end, when we run this calculation, that's going to give us our flux. So this ends up being pi for our final answer. And the important, one of the important things to take away from is that it's bigger than 0, which means that the net flow is outward. If we had a negative, we would have a net flow inward around the substance around the field. So positive versus negative in the context of flux gives us a better indication of how things are going to be, or how the fluid or how the substance is going to flow.